Okay. When we talked about the sample mean, we went through a process where first we defined what we meant by a point estimate of the sample mean. We defined the sampling distribution of that sample mean, how we could use that point estimate and the distribution of the sample mean to come up with a confidence interval for where the true mean lay. And then we looked at how could we use sample information to infer conclusions about the population. We've kind of started off with the same process with the sample proportion. We talked about the distribution of the sampling process for taking sample proportions, how we could use that sample proportion as a point estimate for the population proportion, how we could expand that to get a confidence interval for the true population proportion. And now we're going to look at how can I use sample proportions to infer something about a population proportion or a hypothesis about a population proportion. So our objectives are going to be to again remind you of the logic of the hypothesis testing and to test hypothesis about a population proportion. We're going to begin by setting up an example to help us with the idea of the hypothesis test. And let's say that we collected a sample of 1,000 people and 534 are in favor of banning cell phone use while driving. The sample proportion then is 534 out of 1,000. We'll denote that by p hat. The question we want to know is, does that mean a majority of the population is in favor of banning cell phone use while driving? By majority means, does that mean that more than 50% of people are in favor of the policy? Or could it be that just by random chance, we had a sample that we took that had a proportion more than 50%? So our null hypothesis is that the true proportion is equal to 50%, and the alternative will be that the proportion is greater than 50%. And just as before, we're going to try to take a measurement of, supposing that the null hypothesis is true, how likely is it that we would have observed our particular sample? If it's unlikely we would have observed our sample under the assumption that the null hypothesis is true, we would say we have a statistically significant result. When results are statistically significant, we will reject the null hypothesis. So in this example, we've got a sample proportion of 0.534. If we assume the null hypothesis is true, that the true proportion of the population is 50%, then our sampling distribution would have a mean of 50%, and the standard deviation of that distribution would be about 0.016, using the formulas that we came up with in section 9.2 and 8.2. So now, knowing that the sampling distribution is normal, this is about what that sampling distribution would look like given that the null hypothesis is true. Right? We're assuming that 50% of the proportion of the population will want to ban cell phone use, that's the true proportion. With a standard deviation of 0.016, this is what our normal curve would look like. We know from the normal distribution we talked about earlier, if we're more than 2 standard deviations away from the mean, then we consider that probably a fairly rare occurrence. If we're more than 2 standard deviations away from the mean, then we would say that it is unlikely that we would have observed this by chance. So our assumption about the proportion being 50% is most likely incorrect. So we'll see how many standard deviations is our observed sample proportion away from the hypothesized? So we'll look at p hat minus the hypothesized proportion divided by p naught times 1 minus p naught over n. So that's going to give me a z-score of 2.15. So we know that we are 2.15 standard deviations above the hypothesized proportion of 0.5. Because we're so far away from the hypothesized proportion, we're going to reject the null hypothesis. We're going to conclude that the true population proportion is more than 0.5. And why does it make sense to reject the null hypothesis? Well, if we're looking at more than 2 standard deviations away, that means I only have a little over a 2.28% chance of being more than 2 standard deviations away. Being 2.28% chance that I'm higher than that is a pretty small number. So we know that we would have a 97.72% chance of seeing something less than 2 standard deviations away from the mean. Or less than 2 standard deviations above the mean. In our classical approach, if the sample proportion is too far away from the mean, then we'll reject the null hypothesis, just as what it did before, except for now we're using proportions rather than averages. If the sample proportion, poorly worded statement, if the probability of getting a sample proportion as extreme or more extreme than the one obtained is small under the assumption, the statement in the null hypothesis is true. Okay, let's rephrase that. This whole slide that the book has provided with me is not correct. It should say, if the probability of getting a sample proportion as extreme or more extreme than the one obtained is small, under the assumption that the null hypothesis is true, we will reject the null hypothesis. So if our probability of seeing this sample proportion is small, we're going to reject the null hypothesis. Another approach would be to look at the actual z-score that we get and compute the probability of seeing that z-score, and then use that to determine if it's how likely it is, or if it happens a small amount of the time. In this case, if I look at 0.534, it actually has a probability of 0.0158. So the probability of being greater than 0.534 is 0.0158. So we only have a 1.58% chance we would have seen our sample proportion or something higher. Because that is such a small number, we are not likely to believe the null hypothesis is true. We will reject it in favor of the alternative that the proportion is greater than 0.534. So let's kind of put that together in terms of a formulaic approach, and it's going to be similar to what we did with the mean. We're going to first come up with a point estimate. In this case, it's going to be the sample proportion rather than the sample mean. We know that the sampling distribution will be approximately normal, and that the proportion of the sampling process will close in on the true proportion of the mean. And we have this expression for the standard deviation of that sampling process. We do need to verify that we did take a simple random sample, that we had less than 5% of the total population, that at NP times 1 minus P is bigger than or equal to 10. Because we're assuming the null hypothesis is true, we're going to use the proportion that we're assuming has the characteristic as P naught. So P naught will represent the value of the null proportion. How many do we think, or what percent of the population do we think has the characteristic? We again will have three different possibilities for hypothesis test. Either the proportion is equal to something, or it's not equal, less than, or greater than. The null hypothesis will always still be an equality statement. In this case, it's going to be an equality statement about a proportion. So we're going to have some preconceived idea of what percent of the population will have that characteristic. That's what we will set our null hypothesis to. The alternative will be either not equal, less than, or greater than. That alternative hypothesis will be chosen based off of whether we think it's just not equal, or if we think there's a direction of less than or greater than. We will still do the same process as we did before of picking a level of significance. So we have to pick the type 1 error rate that we're comfortable with. We're now going to compute a test statistic, just as we did in all of our other processes for testing hypotheses. The difference is our test statistic will now be something with a little bit different formula. First of all, it will be a z-value rather than a t-value. And it's going to be related to the hypothesized proportion and the sample proportion in the following way. The z-score will be p-hat minus the hypothesized proportion divided by the square root of p-naught times 1 minus p-naught over n. Again, we're assuming that the population proportion is p-naught, so if that is true, the expression on the bottom is the standard deviation. And just as before, in a two-tailed approach, could go either way. So we'll have to split our confidence or our significance level up in two pieces, and we will either go too far out to the right or too far out to the left, we'll reject. In a left-tailed test, if we go too far to the left, we'll reject. In a right-tailed test, if we go too far to the right, we'll reject. So written in terms of mathematical expressions, if our test statistic is too far to the left or too far to the right, we'll reject the null hypothesis. Again, in a two-tailed, remember that the significance level has to be split into two to allow for an equal chance of going left or right. For left-tailed or right-tailed, we do not have to split that significance level because we have a direction indicated. So for a left-tailed, if we go too far to the left, we reject, or if we go too far to the right in a right-tailed, we will reject. The p-value approach is, again, the same as it has been. We'll still calculate our test statistic using this new formula for the proportion rather than for a mean or even two means as we saw previously. We can then look up that z-score in the table to come up with a p-value associated with that. If it's a two-tailed test, we'll have to double that p-value. If it's a one-tailed test, we can just take the p-value that's there. We can also use StatCrunch to help us out, or our calculator or Minitab, or any number of other statistical tools that will do the test for us. And we'll see some of that in lab. If the p-value is less than alpha, we'll reject the null hypothesis. And just as before, we'll state a conclusion based off of either the fact that our test statistic is bigger than or less than some critical value, or our p-value is less than alpha or not less than alpha. So take an example. In 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In 2007 poll of 1,010 adults, 525 stated they did not trust the media. At the alpha equals 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media fully and accurately has increased since 1997. So again, note the setup of the problem. We have some preconceived idea of what the proportion should be. In this case, we think that 46% of Americans will not trust the media. We're now coming up with a new sample. In that new sample, we have a number that we surveyed and a number that had the characteristic we're interested in that will give us a point estimate for this new poll. We want to know if these results are statistically different than the preconceived percentage that we had. I want to know, has it increased since 1997? So, our null hypothesis is that the proportion is 0.46. Our alternative is that the proportion is greater than 0.46. So P being bigger than 0.46 is the alternative. P equals 0.46 would be the null. We did take a random sample. We've certainly got less than 5% of the population. It does satisfy this rule that n times p naught times 1 minus p naught has to be bigger than 10. So the null hypothesis is that p is 0.46. The alternative is p is greater than 0.46. We picked our level of significance of alpha is 0.05. Notice because we indicate a direction, we have a one-sided test. The sample proportion is 0.52. We take the number with the characteristic out of the total sampled. So the test statistic is 3.83. If we look up the critical value for a one-sided test, z sub 0.05, that's 1.645. Again, one-sided meant all of the significance was going in one section. We could look up z sub 0.05 either from my z table, or I could go to my t table and remember that I have the infinite row. And in the infinite row in the 0.05 column, I see 1.645, so I know that that's my critical value. Because 3.83 is bigger than that, we will reject the null hypothesis. If we go back to our t table, or if we go back to our normal table now, and I look up a value of 3.83 in my normal table, you'll see that our table doesn't even go to 3.8. So it's very unlikely that that will happen. And in fact, if we go down here in the extreme, being more than 3.83 would be less than 1 minus 0.9999. So it's almost zero. So this is approximately zero. So it's very statistically significant. And very strongly then we would reject the null hypothesis and we would conclude that the proportion has increased. So there is sufficient evidence to say that the percentage of Americans that do not trust the media fully and accurately has increased since 1997. That concludes our discussion then of how to do hypothesis tests with proportions. We'll now do some examples with those.